Welcome to day 2 of definite integrals. We're going to start off by doing a review from last lesson. So we're going to calculate the area under each curve for the various shapes, and then we're going to look at approximation given a table of values, and we'll approximate the left hand Riemann sum, the right hand, the midpoint, and also the trapezoidal method. So we're going to start off by just calculating the area underneath the curve. So our very first one, we have a semicircle. And to calculate the area of a circle, we know that is pi r squared. And because we have half of that, we're going to divide that by 2. Now we just need to find the radius. So the radius, remember, is half of the diameter. So this is your diameter, and then half of that will be your radius. And looks like from 0 to 2, your radius is going to be 2. So that's 4 pi divided by 2, which is 2 pi. If you want, you can go ahead and pause this video and find the area for the following two shapes. Okay, so for this next one, the area of the triangle is 1/2 times base times height. So our base is all along the bottom here from -2 to 2. This distance is 4, and that's our base. And then the height of the triangle is 2. So 4 times 2 times 1/2 is 4. And lastly, we have a trapezoid. We just learned how to calculate the trapezoid last time. We need the base, height 1, and height 2. So the area of a trapezoid is 1/2 times your base. That's from -2 to 2, which is 4. And then height 1 plus height 2. So height 1 is 1. Height 2 is 2. So that's 3 times 4 divided by 2, and that will be 6. Now, the next example is exactly like what we did the last time. We were given a table of values. Why don't you go ahead and see if you can calculate the LRAM, RRAM, trapezoidal, and the MRAM on your own, and then I'll go through the solution with you. All right, so remember your right-hand Riemann sum. You're going to compare each interval, and then always pick the left value. So first I multiply, well, because our interval for time is always in increments of 5, so if you look at that from 0 to 5, 5 to 10, 5 to 15, and so on, these are all increments of 5. And then afterwards, I just going to sum up all the left values for the light output for each interval. So in between 0 and 5, my left data is 0. From 5 to 10, my left data is 0.2. From 10 to 15, my left data is 0.6, and so on until I hit 25 to 30, and my left data is 3. Essentially, it looks like I'm going from 0 to all the way to 3, and I'm just omitting that last data point. Then on the right Riemann, again, our width doesn't change, it's still 5. But now I'm going to pick the right value instead of the left. So between 0 to 5, I'm going to pick 0.2. From 5 to 10, I'll pick 0.6. And then all the way to 25 to 30, I'm going to pick 1.8. And essentially, it looks like you're omitting the first set of your first data and then having the rest of them. And you're summing them up. Okay, for the trapezoid, so we learned that the area of a trapezoid is 1/2 times your base. So that's where the half comes from. This is your base. And the rest of this is just the summing up all the different heights together. And I kind of simplified a bit more to make it easier to calculate and faster. So if you look at your height, you're going to do 0 plus 0.2, 0.2 plus 0.6, 0.6 plus 2.6, 2.6 plus 4.2, and so on. And then multiply it by 5.5 at the end. And lastly, your MRAM. We're going to have different intervals here because we're going to go from 0 to 10 so that we can have a midpoint of 5 in between. So our sub-interval goes up in increments of 10. That's where this 10 comes from. Then afterwards, I'm picking the middle value of each. So then your next one's going to be from 10 to 20, and then you're going to pick the middle value, which is a value at 15, that's 2.6. And then from 20 to 30, and that middle value is 3. That's where the MRAM value comes from. Okay, so this is just kind of a summary of what we've done before. Now, in general, we can say this in terms of K and F of CK and so on. So it's a more general description of what we're doing here. So you can read that through. I think it'll just make more sense if I show you in terms of a picture. So essentially, we've been drawing these out, finding this is just an example of LRAM. We would use the intervals found down here, and that would be your C1. So down here is your C1. This is your C2, C3, and so on. Some of these products. What do each of these mean? Well, this is the height of your rectangle, and this one is your width. And all of this is going to be the area. So more specifically, looking back at these C values, the CK, where K is 1, 2, 3, 4, and so on, is your X value in the interval. And we use this to find the height. It should be F of CK. And then this delta XK is the width of the interval. So this is the general formula of what we've been doing, and it goes on kind of forever. It really depends on what function we have and how many intervals we want. So these are the following steps in getting that Riemann sum for some interval AB. Now, we're going to look at this in a slightly different way now. We'll look at definite interval as a limit of a Riemann sum. So there's two options you can look at this. So option one, if you notice in step 2, we didn't care about our subintervals if they had the same width. So if we use notation P to denote the longest subinterval, we can force the longest subinterval length to 0 using our limit of the Riemann sum as described. Or you can make sure the subintervals are all the same width, and then we can increase the number of rectangles to infinity using the limit of the Riemann sum. So this is the number of rectangles as it approaches 0. And this is the number of rectangles approaching infinity. Are we going to use these much? Not in particular, but you should be aware of them and understand what it's saying. So now we're going to look at the notation of a definite integral. So this is the limit definition. We could also write it as so here. And this is how we read it. This is the integral from an interval a to b of some function f of x. In other words, this is the integral of f of x from a to b. So if a function is continuous, then the definite integral will exist, but the other way is not true. We can't say that the definite integral exists, so the function is continuous. So just take a note of that, and we're going to apply it later on. So using definite integrals as an area. So we can define the area underneath the curve y equals f of x from a to b as an integral from a to b. So what we can actually do is also draw pictures of the function and then calculate the area underneath the curve to solve for the integral. And that's what we're going to do in example 1. So I'm going to draw the line 3. And it's just a straight line across. And we want to find the area underneath the curve between 2 and 9. So that's the region that we want. Okay, so it said before that calculating the area underneath the curve is solving for the integral. So all I need to do is find the area underneath y equals 3 between 2 and 9. So if we look at our width and our height of our rectangle, we'll have 7 times 3. So then our integral is going to be 21. For the next one, we have the absolute value. So again, I'm going to draw that out. We're going from -2 to 1. So that's your absolute value. But then we're going to close it off so we can find the area underneath the curve. And it's enclosed by the x-axis in both of these. And you're always going to assume that unless stated otherwise. So we just have 2 triangles to calculate the area for. The first one is 1 times 1 divided by 2, which is a half. And the one on the left, this is going to be 2 times 2 and then divided by 2, which is just 2. So that's 2.5 for B. And the last one here, this is the equation for a semicircle with radius 3. So it's something like this, and then we're enclosing with the x-axis. So the area for a semicircle is pi r squared divided by 2. Our radius is 3 in this case. So overall area is 9 pi over 2. So now you're thinking, okay, well, these are enclosed by the x-axis, but what happens if the area is below the x-axis? Area is usually positive, but in a Riemann sum, we can have negative values if the curve lies below the x-axis. So here's an example of that. We're going to sketch the line 3 minus x. Okay, so you have a y-intercept of 3, and then your slope after that is down 1 over 1. So I'm just going to draw the graph as so. And then we want to go from x equals 4 to x equals 8. So again, this is enclosed by the x-axis. We're going to calculate the area as normal, but instead, our final answer being positive is going to be negative because it is below the x-axis. So we have a trapezoid here. So 1/2 times base, height 1 plus height 2. So your base is from 4 to 8, which is 4. And then height 1 can be the left-hand side here, which is 1. Then the height over here, which is 5. So your area is 12. Now, when we state the final answer, this is going to be -12 because our shaded region is below the x-axis. And we are integrating from 4 to 8 of 3x, 3 minus x. Okay, for example 3, we're going to integrate sine x from 0 to pi, and we also know that this is at 2. But we want to determine the following different integrals from a to e. So if we know that sine x has an area 2 from 0 to pi, we also know that sine x is uniform. That is the same, follows the same pattern over and over again. So here's a quick sketch of it. So if you look from 0 to pi, it's saying that this area here is 2. Now if I'm looking from pi to 2 pi, which is what A is asking for, this area should still be the same as 0 to pi, except that it's underneath the curve, so it has to be a negative. Moving on to B, now we're going to go from 0 to 2 pi. So what I can do is add the area of the region from 0 to pi, and then add the region from pi to 2 pi. So that is going to be 2 plus minus 2, which is 0. Now we're going to look at interval from 0 to pi over 2. Pi over 2 is somewhere around here in this green area. So I just want to go from 0 to pi over 2 instead. And because I know that 0 to pi has an area of 2, but we only want half of that because we're going to go from 0 to pi over 2, so I'm going to divide this by 2, so we're left with 1. Now looking at negative pi to pi, I'm going to need this region here and as well as this region here. So again, this is going to be 0 because I'm going to add negative 2 with 2, and that is 0. Then lastly, this is kind of a trick question, this 2 plus sine x. Later on, you're going to learn about the different properties of these integrals. But really, the only thing we care about is the integral of sine x from 0 to pi, but we know that that's 2. This 2 in the front is just a number, so we can separate our integrals by addition. Okay, so that's just coming from the 2, because the area of 2 is just 2, and then we know the area of sine x from 0 to pi is 2, so this overall answer is 4. Now, you should have a graphing calculator, and your graphing calculator can calculate integrals for you, definite integrals. So if you have a TI-83 or TI-84, the old system, you can follow these steps, or if you have the brand new TI-84, the new system, you can follow this. So you should see in your calculator, if you press math and then 9 for fn int, you're either going to see one of these two. Now, if you want to evaluate something like this, you're just going to move your cursor over the lower bound and put in 1. Then move your cursor over the upper bound and put in 3. Or if you have the old version, you're going to put that in here. And then you're going to type in your function. So you should have the x value inside your graphing calculator to do that. So it'll be x squared minus 2x plus 2 as your function. And then if you have this new system, remember to put the x in with the dx as well. So you just plug and chug into your calculator to figure this out. This first one is 14 over 3. And this next one, you're just going to do 3 plus and then whatever number you found. But altogether should be 4.386. You could also do it by graphing. So on your graphing calculator, you want to press second trace, which is the calc. And then you're going to select 7 for the integral of f of x dx, enter in your lower bound, enter your upper bound, and then the window will show you everything. You could also zoom in. You can press zoom and then zoom 6 to evaluate and look at the whole picture of the integral of 1 to 8 of root x dx. So your calculus should spit out the answer 14.418278. And that's it for this lesson. If you have any questions, especially about the calculator section of our lesson today, please let me know and I can get back to you.